Good morning. Hope you're doing well in our day 2 of the COVID-19 zombie apocalypse. We're going to do a little talk about area, and I'm also going to throw in some parts of parallelograms, kites, and rhombuses that should also be remembered when we're talking about these shapes. So first things, we have a parallelogram. And a parallelogram is a quadrilateral where we have two pairs of parallel sides, so the opposite sides are parallel. And we also have two pair of congruent angles. So this angle here is going to be congruent to this angle here. And this angle is congruent to this angle. So the opposite angles are congruent. Now, the equation for finding the area of a parallelogram, well, we know that the area is equal to the base times the perpendicular distance from the base to the top, and we'll call that height. So area is equal to the base times the height. Moving on to the triangle. Now the triangle is a three-sided shape and the equation for finding the area of a triangle is 1/2 times the base times height. In other words, what you're going to do is you're going to take an exact replica of this shape, and you turn it into a parallelogram. So 1/2 base times height. And remember, the height is the perpendicular distance from the base to the top of the triangle. Throw it over there. A trapezoid is a four-sided figure where you have one pair of parallel sides. So this side is parallel to this side, and that's about it. Now, for a trapezoid, we're going to call this base 1, call this base 2, and the perpendicular distance we're going to just say is the height. So when we take a look at a trapezoid, we're going to approach it the same way we approached this triangle. We're going to double it, flip it over on its side, and create a parallelogram out of it. And notice when you look at the parallelogram, the base is base 1 plus base 2. The area is equal to base 1 plus base 2. And then we have to multiply it by the height. But we don't want the area of this entire parallelogram. We only want the area of half of it. So we're going to divide it by 2. A kite or a rhombus. Now these get a little more interesting. So let's go ahead and draw a kite. A kite is a shape that has two pairs of congruent sides. So in this example, this side is congruent to this side is congruent to this side. And also, this angle is congruent to this angle. All right, so a rhombus can be thought of as kind of like a square that's been tilted a bit. We take a square and we apply a force and it bends the square. So we have all four sides are congruent. And again, we'll have opposite sides are, or opposite angles are congruent. Now for the area, something kind of special happens for both the rhombus and the kite. And I'm not going to show the derivation of it, but both of these shapes have diagonals. You have a major and a minor diagonal. And the cool thing about this is that for a kite or a rhombus, and it doesn't matter which shape it is, and you know, these are still congruent and these are still congruent, so there's the connection between the two. So the area is going to be equal to 1/2 diagonal 1 times diagonal 2. We'll call this diagonal 1, we'll call this diagonal 2. And that's about it. The trapezoid and the kite and rhombus are ones that tend to be forgotten often. For a circle, we have, it's supposed to be red, oh well. So we have the center, we have this as the radius, this distance here is called the diameter, the distance around the circle is called the circumference. And for the area of a circle, the area is equal to pi r squared. And remember that pi is equal to the circumference divided by the radius or diameter. So the circumference of a circle is equal to d times pi. Now we come to the regular hexagon, or sorry, regular polygon. Now a regular polygon is we can have multiple shapes here. We can have hexagons, we can have octagons, we can have septagons, and we can really go crazy with this one. But let's start with a hexagon, shall we? A hexagon, a regular hexagon, is a figure where all of the side lengths are congruent. All of the angle measurements are congruent. And the cool thing about a hexagon is I can break it apart by drawing these diagonals. And I will end up with 6 equilateral triangles. And so we have 6 of these, right? And an equilateral triangle, well, let's call this base. That's not 6, that's a B for base. So if I drop this altitude here, I know this is base divided by 2, which means this height is base times the square root of 3 over 2, because it's a 30-60 right triangle. And so the area of this triangle right here is going to be 1/2, because it's 1/2 base times height. My base is B, my height is B times the square root of 3 over 2. And so multiply those together, and we get B squared root 3 over 4. Now remember, this is the area of just one of these hexagons, or just one of these equilateral triangles. And the area of the whole hexagon is 6 of them. So I'm getting an area is equal to 3 times the base squared times the square root of 3. Now, this is a great little formula that will only work for a hexagon. So there's got to be an easier way. There's got to be a formula that will work for any shape. So I'm going to go ahead and erase this. I'm sure you're thinking, no. And I'm going to introduce the idea that the area of a regular polygon is going to be equal to 1/2 times the base length times the perimeter, where A is the base length, P is the perimeter. And so in our hexagon example, I'm sorry, I made a mistake. Why would you have your base length called A? This A value is the apothem. Let's make sure I'm spelling it right. EM. What is an apothem? Okay, well, going back to my hexagon. If I were to go and draw my equilateral triangles again, the apothem describes the height of the equilateral triangle. In other words, it is the perpendicular distance from the base to the center of the regular hexagon, or the regular polygon. So this here is the apothem. So in solving this, let's say this was 10, just for funsies. So what would the apothem be? Well, half would be 5. The apothem would be 5√3, right? So to find the area, we'd have 1/2 times the apothem, which is 5√3 times the perimeter. Well, the perimeter is going to be 66 times 10, right? That's just 60. All right, so 60 times 1/2 is 30. 30 times 5 is equals the area. Now you'll remember we had earlier said that the area of a hexagon is going to be 3 times b squared times the square root of 3 over 2. Well, let's see if it works. All right, so our b value is 10. So we have 3 times 100, because 10 times 10 is 100, times the square root of 3 over 2. 3 times 100 is 300. 300 divided by 2 is 150 square root of 3. So we showed that it works. And this equation will work for any regular polygon. All right. The one trick on this one is, I should probably spend more time on this, but if it's not a hexagon, you need to use trig to find the angles, to find the apothem. That will be necessary. So a little heads up on that one. All right, and finally, to find the area of the shaded shape. All right, so for this one, there are 2 ways you could go about doing it. Well, really, there are 2. So, no, there's really only one. So I know here that the shaded region is made up of a circle minus a trapezoid. And right now I'm realizing that my trapezoid does not have a height with it, which I'm guessing is kind of going to be an important thing. So let's say that height, just for funsies, is 8 centimeters. Okay, so to find the area, we are going to have to find the area of the circle, subtract that out. Now, I'm not going to do that right now. I will provide the answer at the end of this. For this shape, and this is sort of getting you ready for the idea of integrals in calculus, finding the area of a curved object. We are simply going to have to say that and use estimates. So that's 9. Clearly it's 9. We know that's 3. And then we're kind of left with cobbling together, well, that's almost all 1, right? Just call it 1. Pieces and trying to figure out the actual area of this thing. So I say this and this combined is 1. That looks like a half, right? Add that with another half. That's total 1. And then go through it like that. Let's see what you get. I'm going to pause. I want you to pause the video, try to find the area of the blue, find the area of the yellow, and let's see how you did. All right, so now that you've unpaused it, the blue shape is a very satisfying 186.2 centimeters squared. I feel good about this one. There are formulas to plug it in, and I get it pretty close to an exact answer. For this odd-shaped figure, obviously answers can vary, but you can see how I was crossing out pieces that I had used that weren't full pieces to try to create a whole square. And so you can see I ended up with 12 groups of 1. That's what this was. And then 2 groups of 3 and a group of 9 for approximately 27 units squared.